In this video, I am going to teach you how to use liquid chromatography and mass spectroscopy to analyze and identify compounds. LC-MS is made up of two parts. The first part is high-performance liquid chromatography, and the second part is mass spectroscopy. Liquid chromatography consists of two parts, the mobile phase and the stationary phase. The mobile phase is the mixture that you wish to study. The mobile phase travels through the stationary phase where it becomes separated. The stationary phase contains compounds like the one shown in yellow above that slow down the movement of the mobile phase as it travels through. The components within the mobile phase are separated in the stationary phase based on their affinity to the compounds in the stationary phase. The mobile phase shown here contains three different analytes shown in pink, purple, and blue. As the mobile phase enters and travels through the stationary column, you can see that the analytes become separated and ultimately they are eluted from the column at different rates. In this example, the purple eluted from the column first, followed by the blue analyte, and then the pink eluting from the column last. This shows that the pink analytes had a higher affinity to the yellow compound in the stationary phase, which caused the pink analytes to migrate through the column at a slower rate. As the individual components elute from the stationary column, they can be collected separately from the other components and analyzed individually, which is the main purpose of chromatography, to separate mixtures into their component parts and analyze the component parts individually. Chromatography, in general, separates mixtures based on their various chemical and physical properties, such as size, charge, and polarity. High-performance liquid chromatography is used to separate mixtures based on their polarity. This is an example of a stationary phase column. This column is used for reverse phase HPLC. In reverse phase HPLC, the stationary phase column is lined with a nonpolar hydrophobic resin. This column is packed with silica gel. The silica gel is lined with an 18-carbon chain to prevent the column from becoming polar. Some reverse phase columns have silica gel lined with 8 or 4 carbon chains. The mobile phase is polar, and the polar analytes are eluted from the column first, while the analytes that are less polar or nonpolar bind to the nonpolar resin and migrate through the column more slow. After the analytes come through the chromatography column and are separated, they enter the photodiode array. The photodiode array has a small window that allows light of various wavelengths to travel through it. UV-vis spectrophotometry will be used to detect the analytes. A tungsten lamp is used to scan light in the visible light spectrum, and a deuterium lamp is used to scan light in the ultraviolet light spectrum. These lamps produce light that travels through a slit to the prism. The prism separates the light into spectral color wavelengths. The specific wavelength can then be determined by the second slit. As the analytes shine through the photodiode array, the light is shown through the window and on to the analytes. On the other side of the window is an instrument used to record the light that the analytes absorb. Knowing at which wavelength the analytes absorb light is useful because each individual compound will absorb light at different wavelengths. Next, the analytes travel to the mass spectrometer. In the mass spectrometer, the analytes are vaporized and then ionized. The charged ions are then accelerated by an electric field. Next, electromagnetic magnets are used to create a magnetic field that deflects the ions. When you move a charged particle through a magnetic field, it takes on a curved path and then hits the detector at different points. The amounts of deflection for each ion depend on its mass, and more specifically on its mass-to-charge ratio. The data from the detector will be displayed on the computer in a form similar to this. The y-axis represents relative abundance, and the x-axis represents the mass-to-charge ratio. Each peak represents a different ion and its mass-to-charge ratio. The height of each peak represents how much of that ion is present compared to the other species that were detected. Ultimately, using the absorbance data from the HPLC combined with the molecular mass data from the mass spectrometry, LC-MS can be a powerful instrument used to analyze and identify unknown components in a mixture.